In this work, we are aiming to scale up the cross-source annotation on expert domain data. We all know large data is important for deep learning model. Collecting labeled large data is doable on common object domains, but not true on fine-grained expert domain because labeling needs domain knowledge. To solve this problem, we propose a new approach based on semi-supervised learning and treat cross-source workers as human filters. It's a human-in-the-loop semi-supervised learning method where cloud-source workers act as filters of pseudo-labels, replacing the unreliable confidence thresholding. To enable annotation by non-experts, classes are specified implicitly with positive and negative sets of examples and augmented with explanations. In this way, our proposal leverages the strong low-shot learning and confidence estimation ability of humans to create an intuitive but effective labeling experience. Experiments show that our method greatly outperforms various alternatives approaches in several benchmarks. For deep learning, a large dataset is important. We always pursue a large dataset to improve model performance. This is doable on common object data because data can be labeled on cross-source workers, but not true on expert domain because the classes are fine-grained and the labeling is domain knowledge and expensive. However, this is area of big data. Data volume grows exponentially, so the difficulty is not to collect data, but to get labels. So in expert domain, we usually have a lot of unlabeled data and a small number of labeled data, which is affordable to get labeled from expert. So how can we train a good fine-grained classifier using this data? There have been many different kinds of methods: supervised learning, self-supervised learning, and semi-supervised learning. However, while this method has shown great success in coarse-grained recognition, they have been found not to work well on fine-grained domains. For example, on two fine-grained benchmarks, CVPR bird and fungi, there is a large gap to the supervised upper bound. Our motivation is that now that we have known learning from large label data can work the best, why not pursuing more annotations? So in this work, we propose an alternative solution. We try to make the small label data bigger. We aim to scale up the annotation on expert domain with crowdsourcing. The main idea behind it is to teach or guide lay people to annotate expert domain on label data so that they can provide professional level annotations even if they don't have any prior knowledge. Once the label is provided for the unlabeled data, supervised learning method can be directly applied, which is the most well-explored machine learning method. A typical solution is memorable. Memorable is based on machine teaching. Its main pipeline is when we collect a bunch of unlabeled raw data, we could ask experts to label a small part of it. Because it's expensive, based on the label data, we could train a network and design a short course with a selected teaching set, usually 20 images, and teach cross-source workers to be an expert domain classifier. Once they master the domain knowledge, they can label as much as data we have. When we have the label, the final model can be trained on the whole large dataset by supervised learning. However, for memorable, it's difficult to teach cross-source workers a large amount of classes. Imagine we have to learn from 5 birds to 100 birds classes. It's super hard. We cannot do it from just a few examples. This is partially because humans have short-term memory, which has limited capacity. To solve this problem, instead of training human as a fine-grained classifier in machine teaching, we regard human as binary filters. This is inspired by semi-supervised learning method. In semi-supervised learning, a classifier trained on the label data produces pseudo-label from unlabeled examples. This label can be accepted or rejected by thresholding a classification score. For example, for this query image, if the confidence score is greater than a predefined threshold, we believe it's prediction or bingo. However, semi-supervised learning didn't show good success in fine-grained classification. We think it's because the increased difficulty of fine-grained classification. When the label set is small, the classifier is not accurate, and it's also because well-known inability of deep learning to produce well-calibrated confidence score. However, as we all know, humans have strong low-shot learning and confidence calibration ability. So we propose to replace the confidence thresholding with a human, called human filtering. The difficulty is that the annotator may not know the fine-grained categories. In this example, when we ask them, is this a bingo, they may have no idea. To solve this problem, we propose two mechanisms. The first is to ask a question implicitly by introducing the support set. The support set consists of a positive set and negative set. The positive set has a few images of the predicted class, whereas the negative set has a few images of other classes. Then we ask the worker if you agree the query image has the same class as the positive set. If they say agree, the query image is labeled as a predicted class. Otherwise, we ignore this query image. The workers can also say I don't know if they are not sure. By this way, the annotator doesn't even need to know the bigger class. They just need to compare the visual similarity between the query image to each set. Hence, there is no need to teach annotators classes, eliminating the short-term memory constraint of the machine teaching. We are not to teach humans as the classifier, just to leverage their strong self-few-shot learning ability. We just use humans' feature space and have them decide based on the example of the support set. The second mechanism is to introduce explanation. Because the examples of support sets are still very fine-grained, it might be difficult to identify the discriminative object details, so we use explanation to highlight the informative regions to help the annotation process and improve the accuracy of it. This example shows the importance of support set. In this example, a red-bellied woodpecker is misclassified to red-headed woodpecker by network. An annotator may not notice that red-bellied woodpecker has a partial red head, but red-headed woodpecker doesn't have. The inclusion of red-bellied woodpecker in the negative set forces the annotators to realize that there is a class of birds with partial red head. This makes it clear that the query doesn't belong to red-headed woodpecker and more likely to choose disagree. If no negative set, this information is lost and probably leads to false positive. Like semi-supervised learning, our method is implemented in an iterative, progressive way. At each iteration, we get the pseudo label from each unlabeled example. We generate the support set for those high confidence examples and forward them to human workers. The annotators produce their decisions. A great example are removed from the unlabeled set and added to the label set. Finally, we update the classifier with the currently labeled set. We evaluate our method on two benchmarks, a bird dataset with 100 categories and a fungi dataset with 200 categories. We compare our method to memorable on two machine teaching benchmarks. On butterfly, our method is inferior to memorable but superior to it on gauss. This can be explained by the fact that butterfly dataset is easier, not as fine-grained as gauss. This is confirmed by its relatively high classification accuracy. The worker can truly master the 5 classes, but gauss are difficult, and we should know that memorable is unable to work on any class scale. This is its key limitation. On semi-supervised learning benchmark, our method achieves significant gain over semi-supervised learning method. When we use unlabeled data, the improvement over baseline is more than twice as many as semi-supervised learning. To make a conclusion in our work, we aim to scale up the annotation on expert domains. This is expensive if we ask an expert for labeling. We propose a human-in-the-loop method which regards cross-source workers as filters. Our method has achieved notable improvement on several fine-grained benchmarks. Thank you.